So this video, we will first discuss the performance of M-ary FSK. In the previous video, we discussed the receiver structure, and we will continue from that point and discuss the performance evaluation of M-ary FSK. So by performance evaluation, what we mean here is is that we try to find out what is the probability that the receiver will make an error in detecting a particular symbol transmitted in the wrong way, or what is the probability that the symbol transmitted is mistakenly detected as one of the other symbols. So if, to be more specific, if the symbol corresponding to the signal S0T was transmitted, what is the probability that it will be detected as, say, the symbol corresponding to S1T or S2T, anything other than S0T, the symbol corresponding to the signal S0T. Okay. Now we have the picture of the receiver in our minds, and let's say that we have received this, and this is a sample function of the received signal, random process, and you know what is phi 1t by this time. Nt is the sample realization of the additive white Gaussian noise. And from what we have been discussing so far, you can make out that in this case I am assuming that S0T was the transmitted signal, because you know that S0T is equal to root ES phi 1t plus 0 phi 2t plus 0 phi 3t, so on and so forth. So if it were S1t, then it would have been root ES phi 2t. Anyhow, so this is an assumption. I am assuming that S0T is the transmitted signal, and this is what we receive. Now, because of the branching of the signal which happens, at the receiver, so I will not redraw the picture here, because we have discussed it. If you could just go back to the previous lecture video, towards the end we have discussed it. So if we consider the branching of the signal, we can write that R1 is equal to root ES by root M, or ES by M under root, plus N1 by root M. So what happens here is that I will give a quick explanation without drawing the receiver structure. The signal RT is divided into M branches, and the power gets split equally into those M branches, and consequently the signal energy is getting divided by M, and hence root ES is getting divided by root M, and the noise power variance gets divided by M, and hence the noise random variable N1, which we have obtained from NT, by multiplying that with phi 1t and integrating from 0 to Ts. So this is what we have, and R2 would be just N2 by root M, R3 would be N3 by root M, and so on and so forth. Rm will be, in general, Nm by root M. So in the previous case, towards the end, I had generalized it, so I am continuing with that generalization here, except that I have assumed that the transmitted signal is S0T. So that generalization we will do in a short while once we complete this discussion. So now we can write, remember, this is a sample realization of additive white Gaussian noise of zero mean, and two-sided power spectral density n0 by 2. So the variance of n1 will be n0 by 2. We have been discussing this earlier. Variance of n2 will also be n0 by 2. Variance of n3 will also be n0 by 2. And because of the division by root m, the variance of n1 will be n0 by 2m. Variance of n2 will be n0 by 2m, because the variance is nothing but the power. It gets divided by m because of the branching that happens. So I can now write conditional density function of the random variable r1 given that S0 was the transmitted signal. So I'll just put it like this for my convenience, given that S0. So if you remember, this is the vector representation of the signal S0. It is the same thing, because if we know the basis functions, we can recreate the signal. So I'll put like this: conditional density function of the received random variable R1 given that S0 was transmitted is equal to 1 by root of 2 pi sigma. So sigma is the standard deviation, which will be square root of n0 by 2m, because the standard deviation is square root of n0 by 2, variance is n0 by 2, and because of the branching, the standard deviation gets divided by root m, or in other words, the variance gets divided by m, e power minus r1 minus, so if you see, the mean will be root es by m, whole square by 2 into sigma square, so 2 into n0 by 2m. And of course we can rewrite it like this: simple cancellation, and similarly density function of R2 given S0 would be the same as this, except that its mean will be 0, because if you see, R2 is just n2 by root m, n1 as well as n2 are identically distributed and independent. Of course, so is n3 and nm and all those other n's that we have in between. So same as this, except that the mean is 0. So minus R2 square by n0 by m. I will not write the others, because I will be simply repeating it with R2 replaced by, say, R3, then next R3 will be replaced by R4, and finally R subscript whatever it is will be ending with Rm. So I will not do it, so you can do it yourself, and it's easy to understand. So PR1 given S0 is this, of course assuming that S0 is transmitted. PR2 given S0 is this. PR3 given S0 will also be the same as this. And remember that N2, N3, Nm, N1, all these are identical and independently distributed. So strictly speaking, I can simply say that PR given S0, I can simply write this as just e power minus r square by n0 by m, because it is going to be the same for all the other r's except r1. For r1, the difference is that the mean is different. Okay, now once we have this with us, this information with us, we understand that once this information is with us, we understand that when a symbol is transmitted, of course, when symbol is transmitted means the corresponding signal is transmitted, the receiver can, there are two things that can happen. Either the receiver can detect the symbol correctly, or it ends up detecting the symbol wrongly. So if say S0 T was transmitted, either the receiver says S0 T was transmitted or it says it was something else. So there are only two possibilities. Either you detect it, the receiver detects it correctly, or the receiver detects it wrongly. So to find out the probability of error of detecting the symbol wrongly, what we do is we first find out what is the probability that the symbol is detected correctly. Once we find that out, we can subtract that from 1, because there are only two possibilities to find out what is the probability that the symbol is detected in the wrong way. So let us first find out what is the probability of, in this case, since we have assumed that S0 T is the transmitted signal, we'll find out what is the probability that S0 T is detected correctly. And remember from the discussion in the previous video, a decision is taken. We had broken down the entire decision making process, and we arrived at the conclusion that a decision is taken by the receiver by determining which of these R's, that is R1, R2, R3 up to Rm, which is the largest, and then the corresponding signal was transmitted. This is how the decision is taken. So in this case, since S0 is assumed to be transmitted, the receiver will detect it correctly if all other if all other R's, that is all other R's other than, let me just emphasize it, all other R's other than R1 have a value less than R1. So R2, R3, R4, R5 up to Rm, all of those should take a value which is less than R1. In that, when that happens, R1 becomes the largest, and the receiver will simply say that S0 was the transmitted signal, or equivalently, the decision is arrived at that the symbol corresponding to the signal S0 was the actual symbol transmitted. So a correct decision happens, a correct decision is taken when, or if I put it in other words, the symbol is detected correctly in this case when all other R's other than R1 take a value less than R1. In that case, when that happens, naturally R1 becomes the largest and the decision is taken correctly. In case we were discussing, we had assumed at the beginning of the discussion that S1T was the transmitted signal, then a correct decision is taken if all other R's except R2 take a value less than R2, or R2 is the largest value. Anyhow, in this case, we have taken S0T as the transmitted signal. So we repeat that a correct decision happens when R1 takes the largest value. So the probability of R1 taking the largest value is the same as the probability that all other R's take a value less than R1. So given a value of R1, given a value R1, that is given that the random variable R1 has taken a value, the probability that all other random variables R take a value less than that can be easily computed as shown below. Let's first find out what is the probability that R2 takes a value less than R1. So for R2 to take a value less than R1, the probability of that happening is this. This is the probability that R2 takes a value less than R1, given of course a certain value of R1. This is the probability that R2 takes a value less than R1. You just have to integrate the density function of R2, conditional density function of R2, from minus infinity to R1. So that gives the probability that R2 takes a value less than R1. Similarly, probability of R3 taking a value less than R1 will be the same as this, because R2 and R3 are identically distributed and independent. So R3 taking a value less than R1 will be the same as this with R2 replaced by R3. R4 taking a value less than R1 will be the same as this with R2 replaced by R4. And like this, if I try to find out for each, I will see that it's going to be exactly the same. Only the change is going to happen is in the subscript here. So when I go to the mth Rm, I will get it as Rm square drm. And the probability that all the other r's except r1 taking a value less than r1 will be the product of these, because they are independent. So it is a product of, so this into the same integral with r2 replaced by r3 into the same integral with r3 replaced by r4 into, and so on and so on, so on and so forth, till we reach the same integral with r2 replaced by rm. It will be the product of this which gives us the probability that all the r's except r1 takes a value less than r1. Of course, I don't have to say that except r1, because all the r's taking a value less than r1 is will be the product of these integral m minus 1 times. So if we had m as equal to 3, the specific case that we discussed earlier, then the probability of R2 and R3 taking a value less than R1 will be this multiplied by the same as this with R2 replaced by R3. If M was 4, then R2, R3 and R4 taking a value less than R1 would have been this into the same as this with R2 replaced by R3 into the same as this with R3 replaced by R4. Of course, correspondingly you have to change M, which I didn't say, it goes without saying. So we can now say that probability of the symbol, or rather the probability of all the other r's taking a value less than r1 will be now you can see that strictly speaking in this integral r2 is a dummy variable. If you change r2 as u, the result remains the same. If you change r2 as x, the result remains the same. If you change r2 as r, the result remains the same, which means that the fact that we multiply this with the same as this is r2 replaced by r3 with the same as this with r3 replaced by r4, we do it m minus 1 times, can be easily represented by this raised to m minus 1, because you are simply taking the same number and multiplying it m minus 1 times, which is nothing but the same number raised to the power m minus 1. So we have this as the result now. So this is the probability that all the other r's will take a value less than r1 given the value of r1. So if I say, for example, if I have r1 as equal to 0.01, then this r1 will be 0.01, and this will give you the probability of all the other r's starting from r2, r3 up to rm taking a value less than 0.01. Now to find out, so this is the probability of correct reception of the symbol S0 when R1 is taken at a particular value. Now we have to find out, we have to average this out over all possible values of R1 to get the average, to get the probability of symbol S0 being detected, or the signal S0T being detected correctly, because this is only for a specific value of R1, and that can be done easily by simply, or rather, before that, I have to say that this is the probability of the symbol being detected correctly, the signal S0T or the symbol associated with the signal S0T being detected correctly when R1 has taken a particular value. So we can just rewrite this as 1 minus which is a simple rearrangement. So from minus infinity to R1, I have changed it from R1 to infinity and subtracted it from 1, because if I had done it from minus infinity to infinity, I would have got 1 as the answer. So we can rewrite it like this, and then of course we can. So this is still the probability of all the other r's taking a value less than R1 given the value of R1, and we can now make a substitution here. Let r by root n naught by 2m be equal to y. That gives dr equal to dy root n naught by 2m. You make that substitution and we can write this as equal to, I'll skip that step. You should be familiar with that now. 1 minus q r1 by root n naught by 2m, the whole raised to m minus 1. So we are just rewriting this in terms of the q function. Now, as I said, this is for a particular value of R1. We have to average this over all possible values of R1, because this gives us only the probability of all the other R's being less than R1 given a particular value of R1. So we have to average it over all the possible values of R1, and that is simply done by we should have the density function of R1 here. So I am sure you are familiar with this type of process. dr1, of course R1 here. So when I wrote it here, I missed that R1. So this will effectively be averaging this over all values of R1, because as I said, this is the probability of all the other R's taking a value less than R1 given the value of R1. So you average it over all this dr1 should have been here. There is no space, so I am putting it here. This is the and hence what happens is this is the probability that all the R's, or this is the probability that R1 will be the largest, because all the other R's are less than R1. This is the probability that R1 will be the largest, and this is the probability that the symbol corresponding to S0 T is being detected correctly by the receiver, or the receiver declares that S0 T is the transmitted signal. And hence the probability of the receiver making an error in detecting the symbol S0, detecting the symbol associated with the signal S0 T, or the probability of the receiver not detecting the signal S0 T as the actual transmitted signal will be 1 minus this, because this is the probability of the signal S0 T being detected correctly. So probability of detecting the signal S0 T wrongly as some other signal in the set is 1 minus this, which is equal to 1 minus 1 by root pi n naught by m. This we have taken out of the integration. Of course, this I have taken out, so I don't have to write that again. So dr1, there is a dr1 here, space constraint is there, so I just wrote it at the edge. So this is the probability of the receiver making an error in detecting the symbol S0T. Now, without going into the details, you can easily appreciate the fact that we would have ended up getting the same result if in the first place we had assumed that S1T was the transmitted signal. You can rework the whole thing and see. It's not necessary because of the symmetry that exists and the similarity that exists, because of the fact that the noise which is corrupting these signals is independent of the signal. The noise is always of variance, two-sided power spectral density n0 by 2 and 0 mean. So because of the fact that the noise which corrupts this noise is independent of the signal which is transmitted, one can appreciate the fact that the probability of detecting any signal, not just S0T, the probability of detecting any of the other signals in the set will be the same. So if you try to redo the same analysis, if you try to rework the same thing with say S3T as the transmitted signal, you would have ended up with R3 as equal to root ES by M, phi 3 or phi 2, whatever it is. And the same, you would have ended up getting the same result, except that you would have got R3 here. Or if you had taken something else, you would have got RM or whatever it is. So though we have arrived at this result by taking a specific case as S0T as the transmitted signal, you will end up getting the same result, exactly the same result, with a minor difference wherein R1 will be something else, that's all. You will get exactly the same result if you had assumed any other signal to be the transmitted signal. Now this means that, and since these, it goes without saying, and the assumption that the symbols are equiprobable. In the case of M-ary FSK, you have M symbols and M signals corresponding to them, and the probability of any of these symbols being given out by the transmitter is 1 by M. And since, because of these reasons, the probability of symbol error, the average probability of symbol error will be the same as this, which means that we no longer need this qualifier R1 here. We will be better off by dropping this, because we see that it is not just the probability of detecting S0T erroneously, this is the probability of detecting any of the symbols or signals erroneously, which means that since the symbols are equiprobable, this is the probability of error in detecting a symbol, by the M-ary FSK receiver, which employs coherent detection. Non-coherent detection we will discuss later, and I have already explained what is coherent detection. So this is the performance evaluation, and we will next move on to the next higher level modulation scheme, which will be the quadrature phase shift keying. So the next multi-level modulation scheme that we discuss is the quadrature phase shift keying, or QPSK in short. And as the name suggests, you can see that there will be 4 symbols here. So this is an extension of binary PSK, and now instead of 2 symbols, that is binary bits or 2 symbols, we are going to have 4 symbols, and these 4 symbols can be formed, or you can get these 4 symbols by grouping 2 bits 0 0 0 1 1 0 1 1, as you know. So when you speak in terms of M-ary PSK, M becomes 4 here, because this is a quadrature phase shift keying scheme. And of course it's possible to extend this to 8 PSK and so on and so forth, which we will discuss later. So we Note that this is basically a higher level multi-level modulation scheme where there are four symbols, and since we have four symbols, we need to have four distinct signals onto which we can map these four symbols, because we need four distinct signals now because we have four different symbols, and these signals should be differentiable from each other. They must be distinguishable from each other by through their phase difference. So one way of having this such four signals is as I am about to show here. So we can have S naught T as equal to, we can have S naught T as equal to square root of 2 Es by Ts cos 2 pi FCT plus pi by 4. So Fc becomes the carrier frequency, and then we can have S1T equal to square root of 2 Es by Ts cos 2 pi FCT plus 3 pi by 4. So you can see that between these two signals there is a phase difference of pi by 2, and the third signal in the set will be root of 2 Es by Ts cos 2 pi FCT plus 5 pi by 4. Again, between these two you can see that there is a phase shift of a phase difference of pi by 2, and the last signal, that is the fourth signal, will be root of 2 Es by Ts cos 2 pi FCT plus 7 pi by 4. So we have we can have four signals like this, and you can see that they are the same except for the fact that their phases are different, and they are of energy Es, and the duration of these signals is Ts, 0 to Ts. Now we can express this. So since we have four distinct signals, we can map the four symbols. Say for example, just as an example, 0 0 can form one of the four symbols, and it can be mapped onto this signal, and 0 1 can be the other symbol mapped onto this, 1 0 onto this, 1 1 onto this. This is just an example. That need not be that way, as again we will discuss later. Just to give an example how actually we map it, or just to give an example of mapping those symbols onto these four signals. Now we can express this in a compact form. These four signals we can express in the form of a single expression by writing it like this: SMT equal to square root of 2 Es by Ts cos 2 pi FCT plus 2m plus 1 pi by 4, m taking on values 0, 1, 2, 3. So when m is 0, we get the signal S naught T, which is root 2 Es by Ts cos 2 pi FCT plus pi by 4. When m is 1, we get S1T, which will have 2 pi FCT plus 3 pi by 4. And you can see when m is 2, you will have 5 pi by 4. M is 3, you will have 7 pi by 4. So you can express those four signals in the form of a compact expression like this. And now what we do is, to continue further with the analysis, we will expand this using a very elementary trigonometric identity. So I will write this as equal to SMT is equal to So I will use cos A plus B expansion here. So cos A plus B, you know, cos A cos B minus sin A sin B. So we can write it as root of ES cos 2m plus 1 pi by 4 into root of 2 by ts. So this I am splitting into 2. Root es I am associating with one of the terms of the expansion. The root of 2ts I am associating with the other. Cos 2 pi fct minus root es sin 2m plus 1 pi by 4 root 2 by ts sin 2 pi fct. So if we had this outside and expanded this, we would have got cos 2m plus 1 pi by 4 cos 2 pi fct minus sin 2m plus 1 pi by 4 sin 2 pi fct, and root es into root 2 by ts would have been outside, so we just split it and distribute it like this. Right, now once we have this, we note that, and of course I may not be able to write this always, you have to keep this in mind. We can write this as equal to SMT is equal to S1M phi 1T plus S2M phi 2T, where S1M is this and phi 1T is this. Likewise, S2M is this along with the negative sign. This becomes S2M including the negative sign, and phi 2T is this. And you can see that phi 1T and phi 2T form an orthonormal set of two functions. Energy is 1 and they are orthogonal to each other in the duration Ts. Again, Fc is taken as an integer times 1 by Ts, and these, now what I have here becomes a series representation of the signal SMT. S1M, as I said, the coefficient of expansion, the term which gets multiplied with the first basis function is S1M, which is here, and S2M, the term which gets multiplied with the second basis function, is here, including the negative sign. Now again, of course, just to complete the step, you can write this also in a compact form like this. SMT is equal to summation K1 to 2 SKM phi KT. So our QPSK signal can be expressed in a very compact form like this. Of course, M ranges from, M takes on values, integer values from 0 to 3, including 0 and 3. Okay, now what we do is, we note that there are two orthonormal basis signals, basis functions in our set. And so if I go for the signal space representation, it will be a two-dimensional signal space representation. So we will now draw the signal constellation for QPSK, just as we had, if you recall, we drew the signal constellation for M-ary FSK with m equal to 3, wherein we got a three-dimensional signal space. And in general, if you speak in terms of about M-ary FSK, the signal space will be m-dimensional. So here in QPSK, as we saw just now, the signal space is two-dimensional, and we can draw the signal space like this. You can draw the signal space like this, and once we show the 4 signal points on this, we have the constellation for QPSK, the signal constellation for QPSK. So what we notice is that S naught T is equal to root ES cos 2m plus 1 pi by 4 with m is equal to, of course, so I'll write in general SMT is this minus root ES sine 2m plus pi by 4. Of course, here I have the function phi 1t, here I have phi 2t. So I will not write phi 1t, you know what is phi 1t, it is root of 2 by ts cos 2 pi fct, and phi 2t is root of 2 by ts sin 2 pi fct. So we have the signal SMT like this, which means that S0t will be root ES cos pi by 4 phi 1t minus root ES sin pi by 4 phi 2t. So S11 will be this, and before that I think I made there is some inconsistency in the notation. I don't want to carry it forward from this point. We will correct it here itself. So the inconsistency is that when I wrote when I wrote in the previous, a short while ago, I wrote is this like S1m phi 1t plus S2m phi 2t. So if I go by this notation, S0t will be S10 phi 1t, and S2, this will be S20 including the negative sign. So just I wanted to confirm that. Okay, so that means the signal S0t, the first signal in our set of 4 signals, will have its coordinates. So I have not put equal to is because I'm just going to show what is the coordinates of this when we express this signal as a point in a 2-dimensional space. So its coordinates will be S10 and S20, which will be cos pi by 4 is 1 by root 2. So root ES by 2, and sin pi by 4 is also 1 by root 2. So minus, remember S20 includes the negative sign, minus root ES by 2. So this is the coordinate of the signal S0t when you express it as a point in the signal space, or you express it as a vector in the signal space. So now let's locate this point, root ES by 2. So root ES by 2 on the phi 1 axis, that will be, say, somewhere here. Let's say this is the point, root ES by 2. Let me see whether this writes now. Root ES by 2, and on the phi 2 axis the coordinate is minus root ES by 2. So minus root ES by 2 will be here. So more or less, if I try to stick to the scale that I have adopted here, it will be somewhere here. Minus root ES by 2, and hence the signal S0t will correspond to this point in the signal space. So I will write S0 vector, which is the same as the signal S0t. So S0t is now represented by this point in the signal space diagram. So moving on, when we go for a so remember S1m is root es cos 2m plus 1 pi by 4, and S2m is minus root es sine 2m plus 1 pi by 4. So for m0 we have seen what happens. Now let's see what happens for m1. When m is equal to 1, you can verify that the coordinates will be, so S1t, the next signal, the coordinates will be cos 3 pi by 4, root es cos 3 pi by 4. Root es cos 3 pi by 4 will be minus root es by 2. Cos 3 pi by 4, as you can see, is minus 1 by root 2. Yeah, cos 3 pi by 4 is minus 1 by root 2. So root es into cos 3 pi by 4 gives you minus root of es by 2. And sine 3 pi by 4 will be plus 1 by root 2. And since there is a negative sign here, it will be minus root es by 2. Remember, S2m has the negative sign included in it, as you can see here. Okay. So this is the coordinate of the point corresponding to the signal S1t in the signal space. So that will be minus root es by 2 on the phi 1 axis and minus root es by 2 on the phi 2 axis, which you already have. So this will be S1 or the signal S1t, the point corresponding to the signal S1t, or the vector. When you represent the signal S1t as a vector, this is what it is. And continuing like this, you can see that, in fact, you can see from the trend itself, or you can even calculate. Next, for S2t, it will be cos 5 pi by 4, root es cos 5 pi by 4, and minus root es sine 5 pi by 4, and that will give us minus root es by 2 and plus 1 by root 2 cos sine 5 pi by 4 is minus 1 by root 2. Yeah, and since there is a negative sign here, remember the negative sign is included in the term skm. So the coordinate will be sine 5 pi by 4 is minus 1 by root 2, and since there is a negative sign, you will get plus root es by 2, and this phi 1t coordinate will be minus root es by 2. So that gives us, you can calculate it later, that gives us this as the point for the signal S2. And of course, finally, you will get for 7 pi by 4, you will get it as this. Because cos 7 pi by 4 will be, cos 7 pi by 4 will be 1 by root 2, and 7 sine 7 pi by 4 will be minus 1 by root 2. Because of this negative sign it becomes plus. So you get this. So this is the signal constellation for QPSK. This is the constellation. We call it as the constellation. Probably I have used that word before. I don't remember. If I have not used, remember this is the constellation, the signal constellation for QPSK. The 4 distinct signals are here, and the signal space is two-dimensional. And it is noteworthy that the distance, when you represent this in the form of a vector, the norm is root es, which you can even otherwise verify because this is root or es by 2 under root, and this is also es by 2 under root, and by virtue of simple trigonometry you can see that this is equal to root es. And this being root es by 2, this being root es by 2, this distance will be root 2 es. So this distance will be root of 2 es, this will be root es, and this will be root es by 2, that is es by 2 under root, the whole under root. Okay, now from the discussion which we had till now, it's possible to quickly draw the schematics of the transmitter and receiver. So in this video we will end the discussion after we draw the schematics, functioning of the receiver, and the performance evaluation we will do in the next video. We'll have it in the next video, the next lecture. So quickly, the transmitter schematics will be like this. Multiplier, an oscillator. This will be your main oscillator, which is generating the carrier frequency, and the oscillator output phase shifted by minus, this is a phase shifter, and multiplier here. Let's say this is D1, this is D2, and then we have an adder here. We have an adder here, plus minus. That means whatever we have here is multiplied with a negative sign, and then whatever we have here, it is taken as it is, then added, and you get the QPSK signal here. Now D1 will be plus or minus root es by 2. It will be plus or minus root es by 2, and this will be plus or minus root es by 2. So depending on the symbol on the bit, so plus minus means it can take two values, this can take two values, so the combination together can take 4 different values which form the 4 symbols. And here the oscillator output here will be root of 2 by ts cos 2 pi fct. So we are setting the amplitude such that it's, of course, it's just a scaling factor. So for my convenience, I am just showing that the amplitude is set such that the energy of this is 1. So root of 2 by ts cos 2 pi fct. And after the phase shift here, you will get cos 2 pi fct minus pi by 2. That will give you sine 2 pi fct. So root of 2 by ts sine 2 pi fct. So between these two, the relative phase shift is minus pi by 2, the phase difference. So this is advanced by phase by pi by 2 with respect to the signal that you have here. That's what it means. And it is generated from the same oscillator. And then we have and you just multiply them with this, and you add it, and you get the signal, the QPSK signal. Just to show one example, let's say that it so happens that D1 as well as D2 are plus root es by 2. So you will have root es by 2 cos 2 pi fct here, and minus root es by 2 sine 2 pi fct here, and the two get added and you get the QPSK signal like this, which will be, as you know, root es cos pi by 4 cos 2 pi fct minus root es sin pi by 4 sin 2 pi fct. So what I have done is 1 by root 2 I have expressed as cos pi by 4, and this 1 by root 2 I have expressed as sin pi by 4, and you can see that this will result in, that is, when d1 and d2 are such that they are both root es by 2, the resulting QPSK signal in that signaling interval will be root es. Of course, I left out root, so I should be having root 2 by ts here. I should have been having it here, and I should be having that same root 2 by, because the amplitude is root of 2 by ts. So I have that here as well. I have this root 2 by ts here as well and here as well. So that will give me the signal, QPSK signal in that signaling interval as equal to root of 2 es by ts, that is this and this root 2 by ts which is here, I multiply with this, the root 2 by ts which is here, I multiply with this, I get root of 2 es ts, and then I use the trigonometric identity to end up with cos 2 pi fct plus pi by 4, which corresponds to the signal s naught t. So like this, you can see, this is just an example how the QPSK signal results when this when this schematic works, with an example wherein d1 is equal to d2 is equal to root es by 2. You can put other values and see what you get. Okay, now quickly let us discuss the receiver schematics. So receiver schematics is simple in that this is the received signal split into two. You have to have a local oscillator which is phase matched with the oscillator, because it's coherent detection that we are discussing. Non-coherent detection we will discuss later. It is phase matched with the oscillator at the transmitter, and we have discussed how the phase can be estimated here. In the estimation problems we have discussed earlier how phase can be estimated. That's not directly relevant here, but still we have to understand that at the receiver you need an oscillator whose phase matches the phase of the oscillator, the transmitter. So this will give root of 2 by ts cos 2 pi fct. I am running out of ink here, so let me just complete it. So again, minus pi by 2 phase shift, you will get root of 2 by ts sine 2 pi fct, and they are multiplied here. Of course, RT is split into 2, you just multiply with this, and integrate 0 to ts, sample at the end of integration integrate 0 to ts, sample at the end of the integration, and you will end up getting R1 and R2, or something proportional to R1 and R2. Proportional because I have not considered the splitting of power here. Anyhow, what is happening is that once you have these two, it is possible to go ahead with the decision making, which I will discuss in the next video. So this is the schematic for the receiver. So again, I will quickly explain what are these, because the ink, it's not very the ink is bit dull here. RT split and multipliers here, you have a local oscillator, and the oscillator output here is root of 2 by ts cos 2 pi fct. It is root of 2 by ts cos 2 pi fct, and then that passes through a phase shifter minus pi by 2, and that results in root of 2 by ts sin 2 pi fct. And as it was in the transmitter, there is a phase difference of pi by 2 between these two, again a multiplier, and then It passes through integrators, two integrators, one in this arm, one is in this arm, integrates from 0 to ts. This also integrates from 0 to ts. At the end of the integration interval, you sample. At the end of the integration interval, you sample. You get R1 and R2. And using R1 and R2, it's possible to proceed with the decision making. And that I will discuss in the next lecture.